Hi, this is David Davis, and I'm here with John Dickinson from SwiftStack. How you doing, John?
I'm doing great. Thanks for having me.
Great, great. So today we're going to go a little bit deeper into how Swift and SwiftStack work.
Right.
So first off, we want to talk about the Swift API.
Right.
In a previous segment, we talked about Swift in general, an open source project. It's a object store.
Correct.
And SwiftStack, you guys have created a commercial implementation of the Swift object store.
Yeah, a management control plane that comes alongside of the OpenStack Swift storage engine.
Okay. So how does Swift in itself work?
Right. So I love talking about this.
Okay.
This is kind of what I've been living and breathing for the last several years. So the first thing that we have to start with is, what does the Swift API look like? And when we know what that looks like, then we can see how that fits into the different pieces and what that looks like in a big deployment. So to start with the Swift API, it's all HTTP based. So that means you can use standard HTTP response codes and verbs to talk to it, and you can use you reference all of your data based on a URL. And so this is what an example URL would look like. You talk to your domain, you implement in the actual version of the API. Very consistent version here, but it's always been V1. But the three big pieces of the Swift API are the account, the container, and the object.
Okay.
And so these are really just subdivisions of the overall namespace within Swift. An account stores a listing of all of your containers that you have and some aggregated metadata, like how many bytes do I have stored in this whole thing, how many objects do I have. The container is similar in that it stores a listing of all of the objects, and then it has some aggregated metadata, like how many bytes are in this particular thing. Now, all of these things can store custom metadata as well, so you could say, this container was created on Tuesday, or it contains all of my applications for my FooBar app, or something like that. The object data is where, the object level is where the objects are actually stored. You don't nest accounts and containers, so it gives you a very flat namespace here, but the object is where your data is stored. So you may have an account on a Swift cluster, and you're given an account endpoint. Inside of that, you can create your images container, and then you can upload all of your vacation photos into here, and then directly access those simply with an HTTP GET. You can do a listing of all the objects you have by doing a GET to your to your container itself, and return that back. So the way that that bakes down into the actual logical components of Swift itself is that you've basically got two high-level pieces of Swift. You've got a proxy server, and you've got the storage server. The proxy server is responsible for all of the client-facing communication in the cluster. All client requests come to the proxy server. And then the proxy server implements most of the Swift API, and then it coordinates all the communication with the storage servers. With the storage servers, there's three kinds: the account, container, and the object. So it maps to the account, the container, and the object storage nodes. And so these each are responsible for their respective entity within Swift. Now, the really great thing about this design is that these are just the logical processes that are running. And if you need more, you can add more. So you can scale out, and it's highly modular design. The Unix philosophy of do one thing and do it well means that if you need more client throughput, you can add more proxy servers. If you need more storage space, you can add more object servers. And you can do those independently, so you can very, very specifically tailor your Swift deployment to your specific use case. And you don't have to have this kind of monolithic thing that looks the same for everybody, no matter what they're using it for. Okay.
So for non-developers out there, an API, having an API is a good thing.
Right.
You can communicate with that thing in a standard method. This is really not that different from an HTTP request to a web server. The proxy here is similar in concept to a web server. It's a process receiving communication in and out.
Exactly, speaking in HTTP.
An external source. And then the storage servers down here. Now, is this I guess you could have multiple of these on a physical box?
Yes.
Or for development inside a virtual machine if you were doing some testing?
Exactly right. In fact, what an actual deployment would look like is kind of like this. So you can have, normally a full-featured HA Swift cluster is going to have multiple proxy servers and talking to many storage servers.
Okay.
Now, one of the great things about the fact that you've got this proxy server here is the fact that the storage is going to be, completely private and behind all of these authentication layers, which means that your clients, your mobile phone that's using the Swift cluster can talk directly to the storage cluster. What this means is when you're building out your application, the next greatest mobile phone app, you don't have to scale out your web front-end application architecture just to meet the needs for your storage engine. Okay. You can talk directly to the storage engine, and the storage engine itself, Swift can offload some of the hard problems of storage for you. Okay. So in a real cluster, you've got these processes of the proxy servers, the account servers, the container servers, the object servers, the other back-end components. Those are just processes running on a machine someplace. Mm-hmm. And you can deploy those all on one box, or you can scale it out into something else. And so a Swift cluster, kind of this part right here, is going to have the proxy servers talking to the different storage servers. All the communication comes here. Okay. Now, there's obviously a lot more that goes into a deployment. You've got to worry about identity management with authentication. You've got to integrate that into your existing infrastructure. You've got to deal with load balancing on top of your proxy servers, and how do you actually route this stuff evenly. You could do everything from round-robin DNS to commercial things like F5s and A10s and open source things. The point is that this is a component that has to come in. You've got questions about management, alerting, monitoring, configuration. Mm-hmm. These kind of pieces that come around it is where SwiftStack comes in and provides a lot of value to the OpenStack Swift engine itself.
Okay, so I'm on my mobile phone.
Right.
I'm in an application. I'm talking to some application server, and I'm not pictured here. I click on a music file or a video file. That mobile phone is going to talk directly. It's going to authenticate, perhaps, talk directly to a proxy server, and then just very quickly and efficiently pull out that
directly
file
from the Swift cluster itself, and the proxy server. So it doesn't have to send that internally through. You don't have to scale out your network for your app server because you've already built that out for your storage server.
And I'm completely flexible here, really, in how I design these, how I place these storage servers across multiple physical servers or 2 physical servers, or even perhaps geographically.
Yeah, absolutely.
And I also want to ask you about failure. What if one of these goes down?
Well, that's the failure question is a really good question, and how you build this stuff out. So let me talk about the data placement, and that'll really inform what happens when you have failures.
Okay.
So I'll sketch that a little bit here. The important point about Swift is that today it's a replicated system, which means that if you send some data, let's say you're going to store an image, then it's going to store multiple copies of that image. That provides you both with high availability in case of something going down, but also very high durability, so you don't have to worry about a particular piece of hardware failing and causing you problems with your data.
So if I have to store multiple copies, how is that efficient?
How is that efficient? Well, it really has to do with what is the cost of losing your data? How efficient is it to store just one thing? Right. And especially when you're doing this at scale. If you look at something more traditional, like let's do a RAID 6 volume of something like this. Now what happens when you have one box? I'm going to put a RAID card behind it, and I'm going to use a couple dozen, even just small 2 terabyte drives on 24 servers, and you put a RAID 6 volume on that. You've got some major problems if you have any sort of failure in that. You very quickly reach the end of usefulness on scaling out those. So what's your answer? You start adding more, and what you end up with is these carved off silos of storage that are very hard to expand. By doing replicas, you can fill up the cluster evenly, and you can take advantage of the direct attached hard drives. So here's how this works within Swift.
And when we're storing multiple copies,
right?
I think the important point is you're not storing them on multiple EMC SANs that cost $100,000 each.
Not at all.
You're storing them across multiple commodity
hard drives.
And
servers. Okay. Maybe just some JBODs from Dell, HP, Supermicro, whatever you like to use there. Just use some commodity hard drives, commodity servers that you can use.
And no RAID controllers even?
It depends on your particular use case. Sometimes you might want a RAID controller for a battery-backed cache to protect against some power failures, but you absolutely don't want to use RAID.
You don't need RAID for the redundancy?
Not at all, not at all. Because here's how Swift does that. All the replicas are placed according to a hierarchy of your failure domains. The first failure domain is your hard drive. They fail all the time, so you've got to be able to get around to that. So you want to make sure you have you have more than one copy that are on different hard drives. Servers also can fail, and drives are attached to servers. So it would be really great if you could have those multiple copies placed on different servers.
Okay.
You may actually group your servers into some sort of availability zone of a single failure domain, like a rack is behind a single power supply or single type of rack switch. That can fail. It would be really great if you can put that on multiple things behind multiple failure domains. And then even beyond that, you can have the groups of zones in geographically distinct regions. So here's kind of how that works. If you've got the region at the top, you may have a couple of zones in there. Inside of that, you've got a couple of servers. And inside of each of those servers, you've got lots of hard drives.
Yeah.
So what happens is if you're storing 3 replicas for your data inside of Swift, the way that it's going to be placed is it's going to place those 3 replicas as uniquely as possible across this hierarchy, so that you're going to make sure you have it on different servers in different zones and even if available, different regions. So in this particular example, we've got one region with two zones and a lot of different drives plugged into different servers. So we're going to first make sure it's on different servers, different hard drives. And now, here's your failure pattern. Hard drive died. What happens? You can still have very high availability and durability because you still have your, without having to use something like RAID, because you still have these other 2 copies up. Now, if a server itself failed, it was the server that went down, not just that. In that case, you're still protected all the way up. And that provides you with some really great, that's where you get some of your efficiency. And it's not so much on efficiency on the how many bytes are stored on disk, but let's actually make this usable and more important than storing the bytes on disk. A lot of times it's the making that highly available. You have your data, you need it right now, and you can't have downtime. So you need to be able to do this. Swift works around these failures automatically with very little operator interaction, so that's where you get a lot of your benefits in running a Swift cluster.
Fascinating. What about multiple regions, if you had?
Right.
These are sites, I'm guessing?
Right.
Or they could be sites?
Generally, the way things are deployed is the zone is going to have a really performant network between multiple zones, generally inside of a single data center, or potentially inside of a multiple data centers in a single data center. Something low latency, high throughput, things like that. A region, and Swift supports geographically distinct clusters, so you can, regions generally have an expensive network connection. And that may be cost, that may be latency, that may be low throughput, something like this. But it is absolutely possible to build a Swift cluster today that has data stored both in Europe and APAC and the United States all at the same time, and you get some really great stories with that. There's two really big use cases for using the multi-region support. The first, and kind of the default thing that people talk about, is just a DR story. If one region goes down, I still need to be able to flop over and use the other one right now.
Yeah. And what about latency?
So, well, that's the other big problem is I want to be able to have access to the closest region because I don't want to have a request from London go all the way to my LA office. I want it to go to my Paris office.
Yeah, like I've heard about CDNs on the internet for web content, globally distributed web content.
So that's the fundamental idea behind CDNs, which is a footnote actually integrate exceptionally well into Swift. I've done that at scale a couple of different times. With the Swift storage engine itself, one thing you can do is you can have these multiple active storage regions, request flowing to both of them, and the Swift system is intelligent enough to service the requests from the closest location, which means that you can have access you can be reading data in Europe from your Europe location, and you can be reading data at the same time from Australia from your Australian location, but it's the same logical cluster, and both regions are helping each other ensure that the data is durable and available.
Fascinating. It's
great. It's really exciting.
Really incredible stuff. Well, thanks so much for your time. I appreciate it.
My pleasure. Thanks.
For more information, you can visit SwiftStack.com.